update term in each of the components and GANs, you have to do some tricks there as well. So, but again, it's not that important for now. So main takeaway is that using bandit learning algorithm or adversarial online algorithms, you can train. In principle, you can train GANs very well. And not only it will give you overjumps, not only will give you stability, it can also tackle the problem of mode collapsing. So give you here an example. So if you use classical GAN to train, then in the end it doesn't show you all the modes. It only shows you maybe 1 or 2, 3 here. But if you use Chekhov GAN, in the end you have the whole set. You still have the same. This is a target, and you get the same, almost very similar pattern. So mode collapsing is, I wouldn't say so fully, but in this case it's so. And yeah, so this is just a slide to show that actually the result of Chekhov GAN using bandit theory is not even worse, not much worse, although it tries to keep the mode. And so quality-wise, it's still quite similar. Good. So that was machine learning. So in machine learning, you can use lots of these online techniques on top. Not just for solving core machine learning problems, but also to combine machine learning to tackle all the type of real world challenges. So because of this, now in the next the rest of the talk, I'm gonna show you three different applications where actually using this bandit theory technique, you can really tackle lots of challenging problems that otherwise it was stuck. The people from the field didn't know how to solve them until all the people came with this bandit theory techniques. So let's start with game theory. So in game theory, I already mentioned the result. Like if you have a zero-sum game and both players use learning algorithms to learn, and actually they converge to the stable. And this is exactly the thing that we use in GAN, the previous two slides. Remember? So I already mentioned it, but now I will show you how it works. So this is the definition of two-player games. If you are not familiar with game theory, then I just quickly go through them. So there are two players. They have a payoff matrix. The cell of the matrix is actually a buy matrix. It tells you that how much I will get if I play this strategy, and my opponent plays this strategy. This is the first value. The second value is for my opponent. He could tell me that if he plays this one and I play this action, how much he will get. Okay, so this is a buy matrix. But each cell has two values. In the case of so how to represent this whole game? So you can use vector representation. You can say that if you define one row is action of the row player, then actually you can define a vector with sum of 1 to be the mixed strategy of the row player, meaning that because he can choose randomly, right? He doesn't have to say that, oh, I'm going to choose this strategy, or I'm going to choose this strategy. He can also say that I'm going to choose this strategy with 30%, and then I'm going to choose this strategy with 70%. Okay? So it's like flipping a coin. So you can introduce something called mixed strategy, which chooses randomly between your original strategies, your pure strategies. So now you can use a vector to represent this mixed strategy, and you can also use another vector, y, to represent the mixed strategy of your opponent. And the way you calculate the value is you can use this matrix calculus term. Sorry, matrix algebra term. So if x times n times y is the payoff that you get if you decide to play x, and your opponent decides to play y. Okay? Then you can calculate the same using the pi matrix, the other matrix for your opponent as well. So basically everything becomes matrix algebra, vector algebra. So in the case of zero-sum games, things are a little bit easier because what I get as a reward is what my opponent loses. Right? So basically the two matrices become the same, just with a different side, opposite side. So that I don't need two matrices anymore, I just need two, one to represent the whole game, and everything becomes much simpler. You can drop indexes. But now the goal is the opposite as well. So I say that I want to maximize my payoff, and then my opponent now wants to minimize my payoff. Okay? Think about the gun. Think about the gun. Generator wants to maximize. Distributor wants to maximize the probability of like distribution the two. Generator wants the opposite, wants to minimize the probability of being. So in this setting, in the zero-sum setting, game setting, we have something called the minimax or maximin strategies. Means that I want to minimize my strategy. I want to maximize my payoff, but you want to minimize my payoff. So minimax means that I pay max and you pay min, and you play min against me. Okay? Maximin is opposite. For our player 2, he wants to play the minimum, and I want to play the max. Usually they are not the same in general sum games, but in zero-sum games they are the same. And there's a very nice theorem from John von Neumann back in 1928, saying that if this is a zero-sum game, then minimax and maximin are the same, and they call something called a value of the game. So this is the value of the game, which means that if I play the minimax strategy, whatever you do, I will be at least as good as the value of the game. Okay? So I can always guarantee that my value, my reward, is at least as good as that value. But this is also true for the opposite side, so that if the opponent plays this strategy, that whatever I do, I cannot get better than that. Okay? So it is a stable solution, it's a stable point. And most of the people who want to solve zero-sum games, means that they want to calculate this value. Okay? So solving a zero-sum game in game theory means that calculating this value. Okay. But this is a very difficult problem. In most cases, you cannot solve it computationally efficiently. If you cannot solve it efficiently, can we still estimate it somehow? And the classical solutions are still very difficult. So that's why I said in this case, people decided to use the X3 algorithm. And by using X3, you let each player use X3 to learn which action to play next now, and they simulate the game as a repeated game. Okay? And in the end, once they simulate the game, they stop somewhere, they take the average of the payoff they have achieved so far. Then you can prove that that average is going to be within 1 over square root of t error of the value of the game. Think about the convergence rate. Think about the regret, right? So we can use exactly the same definition as the regret. So think about the best fix in hindsight. In this case, is the value, playing the minimax strategy. You can prove this. So basically, you are converging to the minimax strategy. Okay, on average. That's what you can do with this. Okay. So that's the whole idea behind.